This is a short video that shows how the implementation of these puffs on the FPGAs are done. So, as already mentioned in the presentation prior to this, I've implemented this particular puff in phased manner. Where I started with implementing on 3 series device where we only have programmable logic there. We don't have any process system on it. Then following which the second phase goes with a programmable logic as well as a process system, a software process system there, on which this Arbiter PUF is implemented. And a third one being on a programmable SoC where we have a dedicated processor, and then there is a peripheral like this APUF is created like a peripheral, and then this peripheral starts talking to the processor and does the job of fuzzy extraction or doing post processing on top of the response bit what we get. So this phased manner of implementing it in different FPGAs is done only with an intent that as we move on, the technology improves more further. So when the technology is improving further, we see that the complexity of logic also enhances a lot. So because of which the same puff which is being implemented on a low-end design should be upward compatible to the enhancements that are already been done. So with that note, let me just show you how it has all started. So if I'm going with the basic Arbiter PUF or conventional Arbiter PUF from the literature, the way no literature actually said how the know-how of or it doesn't say how it is built using a Verilog code, but it's all about understanding the concepts, and then there's a study involved there where how we try to place a particular logic on FPGA and then see that how we apply constraints to it and see that the logic that is finally we try to extract the randomness, leaving out any kind of variation with respect to so we have two different aspects when it comes to process variation. So one is going to be random and other one is going to be systematic. Systematic comes up with respect to the fabric on which it is being built, which means the distribution of the dopants around in the silicon fabric, which will lead to kind of systematic variations on top of this particular FPGA fabric. The other one is going completely random, which means it is random and it is deterministic to the specific board. So that way that particular nature is what we exactly try to extract in this particular research. So to start with, we just write a Arbiter PUF code, which Arbiter PUF structure would look something like this. So this is how the Arbiter PUF structure would look like, which has cascaded multiplexers in the following way. So instance 1 is one multiplexer, instance 2 is another multiplexer. They are placed one on the other with common select line. Select line is common for both these multiplexers, while we see that inputs are connected in a crisscross way, where the input that is going to X in the top multiplexer will go, the same input will go to Y in this down multiplexer. So that we see these connections are crisscrossed, and then as and when I am going to give in, and these are connected or cascaded in the following way, which means the input that is being driven into this multiplexer will definitely come out on the last stage of this multiplexer as two different as outputs, but the time it takes for the top row of the multiplexers to generate the output and the time it takes for the bottom row of the multiplexer to generate the output would be little different based on the process variations that come up while these interconnects are controlled by the challenges that are going to come in. So different challenges would give you different paths from the starting input to your final output that is going to come in. That finally leads to an arbitration between the output that is coming between the top multiplexer row and the bottom multiplexer row. And these two outputs, in order to resolve that particular arbitration, we try to connect them to a D flip-flop, okay, where one of them is connected to a clock while the other is connected to a data of that particular flip-flop, so that the arrival time would have a slight difference, which will lead to capturing the response on the output of your D. So that could be like a random response. So it might be like a 0 changing to 1 might be first coming up on the clock, or it might first come up on the DIN. So whichever comes up, depending on at what on the wherever you see the clock being connected. So the moment there is a change happening on 0 to 1 at the clock point, so if there is a 1 on DIN, then 1 is captured. If there is a 0 on DIN, 0 is captured. But the problem is, by any chance, if they definitely there would be a chance of having a violation there, because on the rising edge of the clock there might be a change on DIN. So in order to solve that, we would be capturing it twice. Okay, so in order to do so, we call this as double synchronizer in clock domain crossing concept in your clock domain crossing issues. So to solve it, we use a double synchronizer. So we use a double synchronizer for the same to solve it. So that way basic design has been planned. Okay, and then it is like every time the reason why I'm keeping these keep attributes and don't touch attributes is because every time when I'm going to run it on any other device, I don't want this to be changed by a synthesizer, or any synthesizer for that matter should not touch this particular wires, because if they start touching it, or if your synthesizer starts working on these wires and working on these instances, it finally ends up generating, because for such a design, if a synthesizer starts looking at it, you are doing nothing, there is no logic involved here, it's only about the same path is being taken between two multiplexers. So it literally cuts down the whole logic into just a single instance of this instance 1 and instance 2, and it cuts down all the wires and all the instances. In order for the synthesizer to stop doing it, we start giving this constraints. Okay, so once this is done, we create because this is only, as we see from the structure, this is only going to generate me n challenges while only 1 bit response from it. So 1 bit response is going to be this. So this is going to be 1 bit response while n bit challenges are coming. But in order to make it like a 32 bit challenge and the 30 bit response, I need to have an array of this particular structure. In order to have an array of this particular structure, I need to create a IP for this. So if creating IP is like just we have specific tools right inside Vivado which will create an IP for this. So that IP is somewhere here. So IP is already created with a version. So next step is about creating this array. So that array is created here. Okay. So once we create it, there's a way of then we create a of 32-bit array. Okay. So once we create a of 32-bit wide, that again we need to create a. So after creating a 1-bit APUF IP, we start creating the after we start creating the custom block for it, and then we start analyzing the design. So it is something like this. Let me show you. So a 32-bit PUF. Yeah. So this is how. So this is how a 32-bit PUF would look like. So something like this. So yeah. So this is an array. So each of this is actually a 32-bit. Each of this will become a 32-bit 32-bit challenge while 1-bit response. So we cascade. We take them as an array and finally see that we have the common challenges for all these IPs, while we have 32-bit responses being generated. We concatenate all of them by just finally end up generating a 32-bit challenge and response pair for a APUF. Okay. So once this is done, we create once this is done, we create now that a peripheral is created. A peripheral is created with 32-bit challenge and 32-bit response. A peripheral is created with enable 32-bit challenge and a 32-bit response. Once this is created, the next step is about using this and then creating an interface between the CPU and this particular peripheral, and then we start developing a hardware, initial hardware which has a processor, and then we have an interface, and then we have this peripheral. So in order to create that, we need to do something called create block design. So for doing that, we will create this APUF overlay that is there. Okay. So for doing that, we need to have a custom block design for the same. So when we create a custom block design for the same, we look at it in the following way, like this. Like this is this is the hardware part which we need to design. Manually we need to drag and drop all the components, and then we should start connecting them. Now if you see, this is that 32-bit APUF peripheral which we just created, which has 32-bit challenge and 30-bit response, and this is enabled. So in order to start this process to start sending in this challenge and response pairs, or this is only the hardware right now. So on top of it, we need to have a software layer which will help me to start communicating this. So for that to happen, I should first have my hardware enabled. To enable that hardware, I need to see how this process starts communicating with the peripheral. For that, we need an AXI interface with particular GPIO peripheral interface. So this GPIO peripheral interface will talk to APUF peripheral through processor with an interface like AXI. This AXI is supposed to, this is like the AXI interface which has to configure how many masters and how many slaves we have here. Right now in this particular scenario, we have a single master while we have 3 slaves here. So at any point of time, in fact one of them, in fact if you see, this master should actually try to send in the challenge, and master should get the response back from the peripheral. So that way, that's how we have the GPIOs configured for the same. So one GPIO specifically for response, one GPIO specifically for challenge, and one GPIO for the enable. Of course, in the same GPIO we have multiple channels and we can utilize the same. But for now, for the ease of programming it, I have seen that I have taken care that I have dedicated AXI GPIO given for each of the component what I wanted to communicate. So that is like after doing this, after we create this particular hardware, we have the regular steps of creating a bit stream for it. So after we need to create the first step which we need to do is to create a wrapper for it. So wrapper, once it is created, it creates a wrapper like this, okay, a Verilog wrapper. So which means a block design is now wrapped up with a Verilog skeleton, and then now this Verilog skeleton or a Verilog wrapper that's created need to be synthesized, need to be implemented right on the design, and then need to generate a bit stream for it. So once we generate a bit stream, we'll just try to export this as a hardware. So this is a step which will allow me to take up 3 things onto my onto the FPGA board which I wanted to implement this on, which I call this as overlay. This step is exactly what we call creating an overlay. So once I say a hardware, exporting the hardware, exporting this particular hardware, I have three files which need to be transferred onto my board. So the one would be my .tcl file, which will show me all the steps right from the beginning of what I had done to actually design this particular hardware. Second one is going to be the bit file which we are just generating, and third one will be a hardware handoff file which gives me all the board support package files, which helps a software layer on top of it to start creating a register structure for this and then start doing it. This is important. We see that there is an address editor. If you see, this is where all the peripheral, this is using this particular address editor, we will be able to send in the challenge and response pair. So this will be the address, okay, offset address given here, and through this particular offset address, we start from where we start. The high address is going to be this. So depending on what we wanted to communicate, the addressing scheme goes like this. So this is important for the hardware handoff file. We'll have this information about what are all the registers there through which we can start communicating the data through. So these are all like this is very important for the hardware handoff file. So these are the 3 files which need to be imported, exported into onto the board, or transferred onto the board, so that we can start running a software layer on top of it and then start sending the stimulus into it. So this is the same procedure we follow for a ring oscillator and a conventional Arbiter PUF as well as a proposed Arbiter PUF. So in order to show the proposed Arbiter PUF, so this is a conventional Arbiter PUF, while there is a proposal also. So right now, for which I am writing a paper too, I will be publishing the same shortly. So we have this proposed Arbiter PUF. This is the proposed Arbiter PUF. If I guess, look, this is a 12-stage proposed Arbiter PUF. So wherein here it's again the same structure, but only that because there is an architectural enhancement happening as we move on from one generation to the next generation. Here I instead of just one single multiplexer challenge or a select line, I'll have a 4x1 mux here, which will have two select lines here and two select lines here. So within the same CLB, which is previously generating only a single challenge, now I'm generating there 4 challenges, which is now making my puff much stronger and more resilient to attacks. So that's how this proposal goes in. Okay, so this is the same structure which is built, okay, with an added advantage of improving the challenge space, thus making the puff much stronger, and then the resilience with respect to modeling attacks that happen. So this has been compared with the conventional Arbiter puff. Okay, and then how it is done I have shown in the following video following this. Thank you. So now this is the PYNQ board which I was talking about, on which this particular APUF's overlay is created, and this is from where using this particular external card, I'll be loading the operating system on top of it. And right now it's already loaded, and I just wanted to, and the way how we are communicating the data. So in order to make this as my server, okay, so I can actually use this particular Ethernet port to connect to any of the servers, and then I can do this particular transaction. So I can use this puff itself as a transacting element and then do the job. Like, that is the last part of my research, which is like creating a testbed to authenticate the designs. So how we do that is just what I'm trying to show you now. So now that I have already exported the hardware handoff files that I've created, that I just showed you on the demo, and then in order to directly, and I've already ported them onto this particular environment, or onto this particular board's terminal. So I'll be accessing that. So now if you see, this is like a Jupyter Notebook terminal as like a web server. I've actually created a IP address for this particular board with 10.123.5.43, which will allow me to directly communicate with my device right now. Right now, this scenario is like the laptop is being my server, and while the board is being my host. I mean terminal or the mode. Okay, this is a mode, while this is like my host, and that's the server. So it's something like that. So now if we get in, and if this is like the place where I've kept this overlay is right here, APUF design 64-bit. We have 2 parts in it. One is with the hard macro. So this is according to the methodology what I followed. So 3 things which I've extracted from the Vivado environment after creating the custom design, block design for it, and then we have created a bit file, handoff file, and a TCL file. This will be the same thing even with the proposed design as well. So this is like proposed APUF, while this is the conventional APUF. So conventional APUF is 64-bit, which has 64-bit challenge and 64-bit response, while proposed APUF is 96-bit, which has 48-bit challenge and 96-bit response. So let's first try to see how this works. So with the hard macro based design, let me just show you. So test CRP is a Python file which is created, which will allow me to start running the stimulus and then verifying it. Okay, so you can just see I have this overlay being imported from PYNQ. Okay, and this is where I have my 32-bit this is have my APUF 32-bit bit file, and then this is where I am going to take or create handles for all the inputs what I am going to drive into this particular puff. So yeah, this is it. Now if I just try to run this, so if I wanted to run this, so let me just run it. To run it, I can directly use a terminal to do this. So let me use a terminal only directly. So if I'm using a terminal, I'll be getting into cd/. So inside Xilinx, and then I have Jupyter Notebook. and then I have APUF 64 bit. Just like that. Okay. So I'm getting into that, and inside this I have with HM, so with the hard macro, with the hard macro based methodology, with HM, I'll be having this, and then inside this I see I'm going to have, okay, now let me just run CRP. So I'll just run that Python code which is test CRP, which will help me to run, yeah, right. This should first do the series of initial setup of creating the overlay, I mean the mapping the overlay to the board, and then running this. So probably it is just taking some time, but once it starts, it's about the code is all about sending in the challenges into it, and then capturing the response from the device. So the way how we communicate is through this particular Python code, where we start sending the stimulus into it, or the challenge into it, and then we start extracting the response from that. So before we see how it's running, so I'll just show you. Yeah, this is how what we are trying to do is this. So I can write it into the APUF with this particular handle called APUF_enable. That is coming up from here. So right now APUF is going to have the overlay handle, and that overlay will be like a class with the following objects. So APUF.enable is one object out of that particular class, which is given to this APUF_enable, and that's how we handle all the yeah, see, this is how it starts reading the challenge and response pair. So if I just let it stop, like, yeah, this is how we can see the way how it works. So it gives in all the it gives in a particular, right now it is running. So running for 1000 challenge and response pairs. So it gives you how an enable is generated, and from there how we are generating a challenge and response pair from it. So this is like a enrollment phase, where we start enrolling all these challenge and response pairs into a database, and then we start reusing them while authenticating it as a device. So this is one application of PUF, where we are enrolling the PUF with the challenge and response pairs, and then reusing it wherever we want this authentication to happen. We will be authenticating it with this database what we are going to generate. So let me just stop it to show. Yeah, this is, I just stopped it actually, otherwise it runs for a very long time. So it shows that challenge is going to be that bit wide, and then that's a response. So at any point of time, we see for a unique challenge there should be a unique response, and that defines the uniqueness of the PUF that we designed. And that's how this process of capturing, I mean sending the challenges and capturing the responses come. Yeah, this is the same procedure we follow. We start writing this. So the moment this is done, we start writing this onto a Excel sheet. Okay, so kind of this. Let me show you this. So if you just open this, if you just download this, so let me download this. Okay, so if I just download this, so this gives me this shows this allows me to capture or record all my challenges and responses. Based on this, now I do the prediction on top of it with respect to this logistic regression using the machine learning algorithm, which is told in the presentation. And then we started comparing with conventional APUF resilience to attack modeling attacks, and then with respect to this, we saw the significant rise in the resistance for this modeling attacks. So this is how this particular process of capturing challenge and response is done. Thank you.